All right. Hello, everyone, and welcome to First Saturday Science monthly live stream. My name is Alyssia, and I'm one of the First Saturday Science coordinators. And I'm so excited to be back with you today. This month, we're going to be talking about paleontology. But before we get started, I want to let you know if you're following along with this event to get your water boiling. You're going to need some warm water, or maybe put it in the microwave. All right, so let's get started. Paleontology, what is it? It is the study of prehistoric life or ancient life. And we all know about dinosaurs. Dakota, would you like to tell us about your favorite dinosaur?
My favorite dinosaur is called a Rajasaurus, and it has a horn near its nostril, which is on the tip of its head, and it has kind of like fangs on the front end of its top or upper jaw, and it's fairly big.
All right.
And it's a carnivore.
That's nice. That was all really good information. I had never heard of that dinosaur before, so thank you for sharing that with us. Again, I want to make sure that you have your water either getting warmed up on the stove with adult help or in the microwave with adult help. We did get some feedback from our last event saying that you would like to have a little bit more time to set up the experiment. So that's what we're asking for you to do right now. Because we listen. All right. Paleontology, going from T-Rex roar, to turkey gobble gobble. Let's get started. What is paleontology? Do you know what paleontology is? I kind of just said it earlier.
The study of ancient animals?
Sure, ancient life, prehistoric life. That is really good. You're a good listener. And that could include dinosaurs. That could also include reptiles and different forms of animals, as well as tiny, teeny bacteria even. So it covers a large range, and it helps us understand life on Earth back way back in the day. What do you think paleontologists do? Given that information.
Usually the study of fossils and and animals that lived long ago.
Yeah, exactly. Fossils. So what are fossils? Do you have an idea?
The remains and bones of a dinosaur.
Or anything. Yes, from prehistoric life. You are spot on. Let me get a high five. Awesome. That's exactly what they are. And what do you think of paleontologists' tools? What tools do you think they use?
Hammers, ice picks sometimes, and
chisels,
brushes, water.
Yes. Wow. You impress me every time we do this. You know so much. So I hope your water is warmed. We gave you a little bit of history of what paleontology is and what paleontologists do and what tools they use. And now I'm going to turn it over to Antavia, my colleague, who's going to explain the posters behind us. Let's go. Excuse me.
Hi, everybody. My name is Tavia, as you can see, and I'm here to talk a little bit about slime and amber preservation. So our paleontology unit this month is available in a PDF form. And if you don't have access to that, please reach out to us and we can get you all kinds of fun activities for this month, other than the one that we're going to perform today. And so today, the activity that we're going to focus on is making slime. But before we make slime, we're going to give you a little bit of information about amber preservation, because the slime that we're going to make is going to mimic preserving an insect. And so I'm going to bring you over to our amber preservation board. So a question that I didn't know previously was, what is amber? Where does it come from? Amber is kind of like, it looks kind of like this yellow material. And what we found is that there are preserved insects or plants or birds from a long time ago, millions and millions of years ago. And scientists are able to use that in order to understand what life was like back then, and maybe a little bit about the history, the timeline history of where things kind of fit together. But where did this come from, right? And so where it comes from is from trees. Trees, I'm sure you're familiar with maple syrup and sap. These are things that the trees can secrete in order to move nutrients around its trunk body. But they also secrete just a general resin. It's a little bit different than sap, but it kind of has a similar stickiness and sweetness, and so it attracts bugs. And so what happens is when a tree is injured, like a broken branch or something, then it will secrete this resin. And the resin is really sticky and sweet, and bugs are attracted to it. And so the bugs will land on it, and sometimes they get trapped in it if it's a little bit too sticky for it to fly away from or to crawl out of. And so what happens is that resin starts to harden. It goes from a form that's kind of like honey into a form that's really it's called copal, which is what we call young amber, where it's not like a rock quite yet, but it's still a little bit soft.
It's kind of like water and ice.
Yeah, kind of like water and ice. Exactly. So when things are really loosey-goosey, they're kind of like water. When those molecules are a little bit warmer, they're kind of like water. Whereas ice, like Dakota was talking about, is a solid. And so in order to get to that solid form from that liquid form, it has to undergo intense pressure and intense temperature changes in order to cause the resin to turn very hard. And so what we found is that these trees with these bug specimens that are trapped in this resin, sometimes the glaciers were like these giant ice mountains kind of that moved across the earth a long time ago. Sometimes the glaciers would raise down entire forests or wooded areas and bury those trees with that resin and those specimens deep into clay. And that's where it would interact with this intense amount of pressure and temperature in order to create that hard resin form. And so what ends up happening is a term called polymerization. And that's a big word, but it's really important because what happens is the copal, the young amber, undergoes that polymerization, and it's triggered by that intense pressure and temperature change. And so polymerization is also a really important word for the creation of slime, which we'll talk about in just a second. But I also wanted to mention that science is all about innovation, and it's all about answering questions that we don't necessarily know the answer to all the time. And so scientists are always working. You know, we have books with facts in them that are known, but sometimes we don't always know where those facts come from, or we don't necessarily know the whole picture. So we know lots of fun facts about amber and about insect preservation in amber, but we don't necessarily know exactly how long that process takes. And so that's something that's still being studied. But they have found that most amber is about 30 to 90 million years old. So we know that process takes a very long time to happen. And so this is a great way for us to learn more about extinct species, especially because there are most resin-forming trees are conifers. They're coniferous. They're kind of like fir trees that you might see a lot around the holiday time. They're the ones that have needles when it's cold outside still, rather than broad leaves. But an interesting thing is that most of these ancient specimens are produced by an amber that is secreted by an extinct species. So we don't even know a lot about that tree either. So there might have been some special characteristics about that tree in particular, and its ability to preserve specimens for a very long time. So this is cool. This is a little scorpion, in case you didn't quite see it yet. Cool, huh? And then in case you wanted to see it, this one's a butterfly too. I thought this one was really pretty. And so next we're going to talk about slime, and that's the experiment that we're going to go through today. So while, you know, amber isn't exactly the same as slime, obviously, we can make it in about a minute. It doesn't take millions and millions of years. But your take-home science kit has glue that's been pre-dyed with an orangish glow, so it kind of looks a little bit like amber. So we're going to just kind of play around with the idea of polymerization. that won't take millions of years to produce. That way we can do it in lab. And so slime. What is slime? Dakota, do you know what slime is?
Like a not sticky blob of liquids and solids.
Yep, a not sticky blob of liquids and solids. That's a really good way to put it. Because so most things on Earth exist in about 3 different phases: a solid, a liquid, or a gas. A solid is something that maintains its shape no matter what you do to it, unless you like break it or something. It's going to stay in that same shape, kind of like this little dinosaur model. We consider this to be a solid because it doesn't pool like an ice cube might melt, you know. Here, you can take that. And then a liquid is something that takes on the shape of its container. It's going to act with gravity. It's going to go down wherever it is. It's something that you can pour. And then a gas is something like oxygen gas in our atmosphere, what we breathe. Gas is going to take up the volume of the shape of its container, not just horizontally, but vertically as well. So in solids, particles are packed very tightly together, and they're packed so close that they don't really change shape unless that outside force is put upon it. Whereas in a liquid, the particles can move around each other and take the shape of the container. But slime is very interesting because it actually doesn't act exactly like a solid or a liquid. And there aren't a ton of things in our world that naturally act like that. It's called a non-Newtonian fluid. And that's because it can be picked up as if it's a solid. It can maintain its structure a little bit. But at the same time, it will ooze kind of like a liquid. You could, if you are patient enough, you could press down into it as if it were water. But if you hit it really quickly, it's going to act like a solid. You're not going to be able to go right through it if you're very quick. You'll notice that slime will take the shape of whatever container that it's in, but it can also act like a bouncy ball too because it's very elastic. And this is because of polymers. Slime is made of polymers. A polymer is a very large chain of molecules. And I'll show you here. These are the polymers, kind of like a visual representation of what a polymer and glue might look like. They're these long chains. They're kind of loosey-goosey, as a liquid might behave, right? You can kind of move through them very easily. And then our slime reagent that we're going to be using is going to be borax. And borax, you can see, is kind of like these little molecules. And so when they're cross-linked, they can act kind of like bridges. Think of like my arms as the polymer chains, and then all of a sudden you have these borax molecules that are holding them together. So they can still kind of move a little bit noodly, but they're still attached. They're not going to be separated like a liquid would, because you would be able to put your hand through a liquid, but this way you're not going to be able to do that right away. But you can still convince it to a little bit because it still has some of that wavy nature. And so before we get started on making slime, I'm going to ask Dakota about his safety protocol. So Dakota, what are you doing today to keep yourself safe in lab?
Wearing goggles and putting on these jackets.
Yep, lab coats. And I have long hair, so I'm going to put my hair back because I don't want my hair to get in the way. And then an additional step for this lab, which aren't in all of our labs, but because borax can be an irritant, it's perfectly safe, but it can cause some slight skin irritation. So I'm going to have Dakota put on these latex-free gloves. And there's a pair of latex-free gloves in every single kit that we have for the take-home kits. And then we'll get started on our experiment. And I hope that your water is warm. It doesn't have to be boiling or anything. It just speeds up that reaction, right? So when we warm something up, we're going to increase the kinetic energy of that system, like water. And those molecules are going to be a lot easier to convince to melt something, which is what we're going to be doing today. Wonderful.
All right, and if you can hear my voice, this is Alyssia. I'm letting you know that we're going on a little bit of a ride.
All right.
Wasn't that fun?
That was fun. Thank you. So the first step is always to look at your experimental procedure. So this highlights all of the materials that you have in your kit, as well as the experimental procedure. So we're going to keep that close while we go through. So step 1 says pour the bottle of glue into the empty container. So I'm going to have Dakota do that. And this is our glue. We're using a polyvinyl acetate glue, also called PVA glue. And I've put a little bit of the illustration of the molecule on here. And you'll just unscrew that and pour that right to the container. Oh, yeah, just take the whole cap off. Got it? It can help too.
Good.
It's okay.
Entire bottle.
Yeah, the whole bottle. We're just going to put the whole bottle in there. And then next we're going to put half a cup of warm water in. And half a cup is about 4 ounces. So this is our pre-warmed water. And I'll show you on here. I don't know if you can see it very well, but there's a 4.0 here, and that indicates 4 ounces, 4 fluid ounces specifically. And 1 cup is about 8 fluid ounces. So half of a cup is going to be how many ounces, Dakota? 4 ounces. So put your first container down. Yep. You always want to measure with your container flat on a surface. Otherwise, that measuring line is going to be a little bit harder to see if it's moving around. That's good. And then we're going to pour that water into the glue. And then we're going to pour another 4 ounces of water. And then we're going to put our borax crystals into it. And so what we'll make is a solution. It'll start out as 2 things, the borax crystals and the water. And as it melts, it's going to create a homogeneous solution. And that will be our borax solution, which will act as our slime activator in this experiment. And you can use this stick to stir the borax crystals. And this is the point where having warm water is super helpful, just to help melt those borax crystals a little bit faster. Because borax does not like to melt in cold water because it doesn't have that increased kinetic energy available to help solvate it. A little bit of patience is helpful here too. While we let that sit, we're going to stir up the glue and the water solution until it's homogeneous. And when something is homogeneous, we say it's homogeneous when it's one consistent consistency, meaning there's no layers or chunks. It's all the same texture, same color. An example of a non-homogeneous mixture would be if you mix oil and water, they kind of separate and they don't like to mix together. Does that look homogeneous to you? What do you think? A little bit more. A little bit more. Okay, perfect. And now let's mix this just a little bit more, the borax, because there's still some crystals. I don't know if you can see in there. Yeah. And it can be as melted as possible. It might take another minute here. Why don't you tell us some more dinosaur facts, Koda, while I finish mixing this? Oh, here's a good one. What's the difference between an herbivore and a carnivore?
Carnivores eat meat and herbivores eat plants and grass.
Yeah. Is there another common diet for dinosaurs that you can think of other than herbivore and carnivore, or one that kind of fits into one of the subcategories?
There's only 2 dinosaurs I know that do this, but there is omnivore dinosaurs,
Omnivore dinosaurs.
which are carnivores and herbivores.
Oh, are humans? What are humans? Do you know what humans are?
Omnivores.
Yeah, humans are omnivores because we like salads and sometimes hot dogs, all kinds of foods. We're pretty lucky that way. We've got all kinds of teeth. Because herbivore teeth have kind of like a flat shape to them, and carnivore teeth
are like knives.
Yeah, they're like knives. They're very pokey. Whereas humans have both because we like to eat all kinds of stuff. Okay, this looks pretty good. So why don't you pour a little bit of that, not all of it, maybe like a fourth of it, of the borax solution as slime activator into here. It's gonna start reacting right away. You can kind of see, oh, look at that texture change. Oh, yeah, sticky. So you don't want to add all of it right away just because you might not need all of it. And the more activator you add, the stronger those bonds are going to be, which means stiffer slime. So if you want really ooey gooey slime, you're not going to add a whole lot of activator. And if you want a very sticky or a stiff slime that you can kind of crack apart, then you're going to add a lot of activator. Oh, look, it's definitely gooey. So before we add a little bit more, I want to show you kind of what, like, I was talking about young amber. It's called copal, where it's a little bit runny, right? And so here we'll act like this petri dish is a tree with like a little bug on there, right? And what happens when it's very runny, it's gonna run down and catch that bug, right? So that's kind of how that young amber, that copal, that resin rather might look. And then when it's sticky, it can hold on to the bug, right? All right, let's keep mixing. And I'm gonna add a little bit more. Oh yeah. Oh, that's good. Yeah. Add a little bit more activator.
That might have been too much.
How does it feel, Dakota? Does it feel
really
different?
Thick. It feels really thick.
It's really thick.
Dinosaurs also can fit in the amber, like this one.
Oh yeah. Yeah, if we had a small enough dinosaur, perhaps we could have some dinosaur amber preservation species. And at this point, you can use your hand, Koda. You got gloves on. Go for it.
It's almost sticky like a big gooey spider or something.
So you can see a little bit better. Look how slimy and sticky. And that's it. So in your container or in your take-home kits, you'll have one of these containers, and then you'll also have a little lid in there as well. So you can play with your slime however you want, whenever you want, and then just close the container for safekeeping, kind of like a container of Play-Doh. And if you have other toys, you can always pretend to fossilize those as well. And then one great thing about this reaction is that the borax is no longer caustic to your skin. So it's totally safe to use your hands as long as that borax is effectively mixed in and you've kind of created that homogeneous mixture.
All right, everyone, this is Alyssia again. We're going to go on another ride. So bear with me. We're going on a ride together. Perfect. So while they go ahead and focus on cleanup, I'm gonna go ahead. Hi, it's Alicia, and I may have changed. If you notice, I took my glasses off, just in order to be able to see myself better because it was a little bit foggy, mask and all. So I'm wondering, what is your favorite part of the experiment or what we learned today? Dakota, what was your favorite part?
The slime part.
The slime? You love slime?
Yeah.
I love
especially
slime
like
too.
putting the bug in it.
Yeah. I loved learning about amber. Honestly, I didn't know much about it until my colleague Antavia described how injured trees kind of secrete resin, and then that resin hardens into amber, and then you can have preservation within the amber. So that's really cool, and that was probably my highlight for today's experiment. So around 6 p.m. tonight, if you are part of our virtual workshop, you'll receive an email from me with the rest of our experiments that you can look at and go through for the rest of the month. So I hope you enjoyed this live stream, and I hope that you come back next month. I'm gonna slide out and let everyone else say goodbye.